Hello guys and welcome back to Counter 10. My name is Ani and on today's episode we're going to be covering the topics of suction and scavenging as well as electrical safety and diathermy. Now this is our second episode in our series of equipment and safety, and while I agree this might not be the sexiest topic, if you ever when you finish your training go out and do rural work, these are the topics that actually help you make sure you can set up an operating theatre environment safely. And because of that, if you can learn these topics well now, they actually pay huge dividend for you in your future career. Now I also know that we're in Viva season at the moment, and I'll be releasing over the next couple of weeks some live practice Viva demonstrations just like the previous sittings. But for now, let's cover today's topic and dive right in.
1, 2, 3, 4.
The first learning objective for today is outline how medical suction is generated and how to set up and test suction systems, both fixed and portable. Suction is one of those equipments that we use every day, and they can come in two different ways. Broadly speaking, you can have stationary or wall-mounted suction, which is what we see in our main theatre environment, and you can see that on your back wall where you have the label of suction. Or you can get portable suction systems, the ones that you take with you when you're transferring a critically ill patient. Regardless of the type, each suction system has the same essential components that ensure it works safely. And these components are a source of vacuum, a collection vessel or a reservoir, and then a delivery tubing. Within each of these three key components, you've got added components which increase their safety. So these are things like filters, which aid in preventing contamination, pressure gauges, which allow us to know exactly how much pressure that suction device is generating, because as obvious as it sounds, too much pressure can damage tissues, and too little pressure is not enough to appropriately use the suction machine. Within Australian standards, for medical suction equipment, they say that pharyngeal suction equipment should produce a minimum free airflow of 20 litres per minute and develop a vacuum of at least 40 kilopascals within 10 seconds. This is roughly 400 millimeters of mercury, and you can check this via either checking the pressure gauge within your anaesthetic machine, or if you take off your yanker and you place the tubing directly onto your hand or your arm, you can feel the power of the suction, and you can also check the corresponding pressure gauge reading. So then what are the principles behind making sure a suction device works appropriately? And for this we go back to our three essential components. Firstly, looking at the vacuum itself. Now vacuum is just an interchangeable word for saying negative pressure, and for a suction device you can have many sources of vacuum. A vacuum can be generated either through electrically powered mechanical pumps, gas-powered pneumatic pumps, or manual pumps. And within the operating theatre itself, the suction here is generated through the electrically powered mechanical pump. Here on the wall you can see the suction devices as outlets, and this is connected to the main facility major vacuum device that's probably located somewhere in the dungeon of your hospital. Now there's many types of electrically powered mechanical pumps, and you don't have to know the exact names of each, but it's most likely going to be a rotary vane pump. Regardless of the type, the principle of the vacuum is the same. For a long time, I used to think that suction worked by generating enough power to pull things into the reservoir or the disposable can. But that's the wrong way to think about it. The power is generated to expel air from that vacuum. By expelling air, you create a vacuum, i.e. a negative pressure area, which is what you then use as the power source to then make your suction device work. So for any type of suction, when we're thinking about what vacuum it uses, it doesn't matter which one it specifically uses, but you realize that all it's doing is dispelling air to create an area of negative pressure, and that area of negative pressure is your driving force to then suck up the debris. And you don't always have to use electrical power to generate that vacuum. you can use gas itself to generate that vacuum. And this goes back to what we discussed previously when we talked about things like the Venturi effect and the Bernoulli principle. We can utilize these physics principles by using things like air and pushing air through a narrow constriction, which then creates a negative pressure, and that negative pressure again can be used as a source of your suction. This, however, is not commonly done, especially in a big hospital, because it's just going to waste a lot of gas. But when you're in a rural setting and you might not have a central facility vacuum, you might use this as your main source of vacuum. And for this, you then need an air cylinder to ensure it works appropriately. Then your next essential component is your collecting vessel or your reservoir. This is what you see normally in a theatre setup. You have your collection canister next to your anaesthetic machine, or on the surgical side, they have the multiple collecting canisters. And again, the key thing here is recognizing how a suction device works, because if those things aren't tightly put on, then you're exposing it to air. And remember, you're trying to get rid of air within the vacuum. That's how the suction device works. That's why if things aren't tightly sealed, our suction doesn't work effectively. The only other thing to consider with the reservoir is that you want it to be an ideal size. So it's the balance of not making it too big that's going to take a while to generate that negative pressure to allow the suction to occur, versus making it too small that you have to rapidly change it over and over again. Finally, the last essential component is a delivery tubing. This is typically a standard tubing that connects the reservoir to some kind of endpoint where you can suction out all the debris. For us, it's either going to be connected to a rigid sucker known as a yanker, or a flexible sucker such as the ones we can use going down into the lower airways. There's nothing fancy about the yanker or the flexible sucker. The key thing again is that you want to make the device safe enough that it doesn't collapse within its own negative pressure, and within the flexible sucker, it has a safety feature. As you might note, it has a little aperture on the side which exposes it to room air. This is there so that you're not constantly putting a high degree of negative pressure at the end tip of that catheter, because as you're blindly poking that into, say, a little baby, that can be a huge area of negative pressure that can create trauma. So what that little aperture does is that if you leave it open, you can safely place the catheter to the point where you want to suction, and then close that aperture to then generate the negative pressure. This is not the Venturi effect or the Bernoulli principle. This is just a safety feature of that flexible sucker, and think of it more as if you're closing the whole system. A good clinical tip to figure out what size of flexible catheter you should use for what patient is double the endotracheal tube size. So that's suction in a nutshell. And that moves us nicely to looking at our next learning objective, which is outline the hazards of anaesthetic gas pollution and methods of scavenging anaesthetic gases. Scavenging is the collection and removal of waste anaesthetic gases from the operating theatre. Sometimes you hear the term decreasing pollution. This technically refers to decreasing pollution within the theatre working space. These gases still need to end up somewhere, and they end up in the outside environment, so they're still causing pollution outside. The reason we want to decrease their exposure within the operating theatre is because different countries have different safety guidelines on how much exposure we should be having from each certain gas. In the UK, they recommend over an 8-hour period, you should have less than 100 parts per million exposure of nitrous oxide, less than 50 parts per million exposure of isoflurane, and less than 20 parts per million exposure of sevoflurane. The reason these guidelines come about is because there's some linkage between higher exposure and increased chances of infertility, miscarriages, increasing the rate of certain cancers, and congenital abnormalities. The overall evidence for all of this is low, but this is why scavenging is an important safety part of our curriculum. Now, in terms of classifications of different methods of scavenging, this can be broadly classified into an active scavenger and a passive scavenger. These can further be subclassified into an open system or a closed system. As the name sounds, an active scavenger uses a pump to generate a pressure gradient to drive out the waste gases, while a passive system uses the positive pressure generated by the breathing circuit itself to drive flow. You won't really see passive circuits anywhere within your major hospitals because they're no longer recommended, and that's because they have lots of inefficiencies. The main disadvantage of them is that they increase resistance to expiration and are a risk of complete obstruction. They're also the least efficient type of scavenging method. In comparison, active systems can work across a wide range of flows, and these are the type of systems you see on your everyday anaesthetic machine. If you look on the side of your anaesthetic machine, it says AGSS, which is the Anaesthetic Gas Scavenging System, and within that you have a little bar where it has the green bar where the scavenging should sit, and you can either adjust the scavenging on that bar itself or on your central boom. And I encourage you to look at this the next time you're in theatre. Just like we talked about with suction having some essential components, scavenging also has some essential components. The mnemonic I remember for this is collect the rubbish drugs. Collect stands for the first part, which is the collection assembly. The refers to the transfer tubing. Rubbish stands for the receiving system or the scavenging interface. And drugs is the disposable system. These four components are going to be the same whether you have an active scavenger or a passive scavenger. So let's go through them in a step-by-step manner. Starting off with the collection assembly, which is where you collect the waste anesthetic gases. This is located within your breathing circuit next to your APL valve. It's prior to the CO2 absorber, and it's located there specifically so that waste gases may pass through the APL valve or the APL bypass valve if the ventilator is working, so that it doesn't collect the fresh gas that's been put into the circuit and it doesn't overload the CO2 absorber. And therefore, it's an ideal location to have your scavenging system. Then you have the next component, which is the transfer tubing, which simply just transfers the waste gases into the receiving system / the scavenging interface. The specific thing with the transfer tubing is that it's a certain diameter of 30 millimeters to ensure that you don't get any accidental cross connection. From here, you get to your receiving system, aka your main place where your scavenging is working. If you have an active system, essentially here, this is working the same way as a vacuum works for a suction. A pump is used to generate negative pressure, which can achieve peak flow rates up to 130 litres a minute. These flow rates are higher than the average flow rates of waste gases, but they don't produce high pressures. The reason why you don't get high pressures is because these active systems are open systems, which means they have small apertures which entrain air to decrease the pressure buildup within the scavenging / receiving interface. And by having this interface exposed to air, aka being open, the negative pressure buildup becomes negligible, and therefore the risk to the patient itself of getting barotrauma or experiencing high either positive or negative pressure is very low. So therefore it's a very safe system to have, but it's a system that requires electricity and power and therefore costs money. In comparison to a passive system, the scavenging interface for these has to be closed, and it's closed because it's relying on that positive pressure generated from the breathing circuit to drive flow. So within these systems, there's a higher risk of barotrauma, and therefore the safety mechanism here is that they have either positive pressure relief valves or negative pressure relief valves. The positive pressure relief valves are set to pop off at greater than a pressure of 5 centimeters of water, and the negative pressure relief valves go off at a pressure of less than negative 0.5 centimeters of water. Then you have the last component of scavenging, which is the disposal tubing. This is the conduit which moves that waste anesthetic gas to the external environment, typically located at the top of your hospital, releasing that gas into the external environment. And that's a nice segue to look at the second part of this learning objective, which is the hazards of anaesthetic gas pollution. Over the years, this has become more of a hot topic, and ANZCA released its position statement in 2019 on environmental sustainability in anesthesia and pain medicine. And the reason I bring this up is because the following year in 2020, it had an SAQ exactly on this, which we'll review in our second part of this episode. The main points from this position statement is recognizing the key terminologies such as global warming potential, or GWP, which is a measure of how much heat a greenhouse gas traps in the atmosphere over a specific time compared to a similar mass of carbon dioxide. CDE, which is the carbon dioxide equivalent, and then you can apply different years to this, and typically you have the CDE20, which is the carbon dioxide equivalent over 20 years, and this allows you to then compare the GWP20 to the CDE20. And then you have the last term, which is LCA, which is a life cycle assessment. Essentially, an LCA refers to the environmental footprint arising from the extraction, manufacturing, transport, use, recycling/waste, disposal, and reuse of the equipment that's made. All these terms can get confusing, and the position statement is quite long, but the main things you have to realize is that whether you're a TIVA fanatic or a volatile fanatic, both options have an impact on the environment. Either the volatile itself has a huge global warming potential, or the volatile causes ozone depletion. Now, with regards to global warming potential, any agent that absorbs infrared radiation that would otherwise leave the Earth is considered to have an environmental impact. And all of the volatile anesthetics and nitrous oxide do this. The global warming potential is highest for drugs like desflurane, followed by isoflurane, followed by nitrous oxide, and then least for sevoflurane. Additionally to their global warming potential, some gases can also have an ozone depletion effect. For this, the worst gas is nitrous oxide. It's a major ozone depleting substance and often considered the most important industrial emission causing ozone depletion. Now, we as anaesthetists actually use very little of the total nitrous oxide within the hospital environment, but it's something you need to be mindful of whenever you're using it. Other gases that can cause ozone depletion are halogenated agents such as isoflurane or halothane, and isoflurane is still sometimes used. However, its contribution to ozone layer destruction is very minor compared to nitrous oxide. The interesting thing is with volatiles such as desflurane and sevoflurane, they don't seem to have any ozone destruction properties. Now, when I was reading this document and to help me prepare for the exam, I just remembered some simple numbers to help me remember which gas was the worst, because sometimes this can come up as an MCQ. Remembering that desflurane at 6 hours of use is equivalent to 1,000 kilometers of driving, nitrous oxide at 50% use is equivalent to 500 kilometers driving, and sevoflurane at 3% use is equivalent to 50 kilometers of driving. Isoflurane sits between nitrous oxide and sevoflurane, and I remember even seeing this MCQ within my Part 2 exam. Now, like I said, whether you're a gas user or a TIVA user, TIVA also has some environmental impacts, and that's when we talk about the life cycle assessment. So it's not just about reducing the gas we use in the operating theatre, it's thinking about all the things related to using TIVA, like the pump sets, the pumps themselves, the syringes, how we dispose of propofol, whether propofol going down the drain is toxic to marine life. All these things are important considerations, and to date, to my knowledge, there's no concrete evidence which tells you to use one anaesthetic over another. So this completes our first section of our episode today, which was suction and scavenging, and moves us to now look at electrical safety and diathermy. When it comes to electrical safety, there are 3 learning objectives which cover broadly the basic physics behind electrical concepts, micro and macro shock, and then the prevention and management of fires and explosions. You can easily ask yourself, why the hell in our curriculum do we have to learn about electrical safety? But the rationale that I put to myself, if you think about the operating theatre being your workspace, it would be very reasonable for you to know everything about your workspace. And that's why these kind of left field learning objectives exist in our curriculum. Now, I'm no expert at electrical safety, so I like to keep it really simple when it comes to understanding. When we talk about electrical supply to the operating theatre, what we have is the power supply coming from the power stations at very high voltages in the multiple hundreds of kilovolts that reaches the power points we see in our operating theatre. At these power points, the voltage here is 240 volts, and it's been decreased from those high numbers through a series of step-down transformers. And this output supplies electricity at 50 Hz at an alternating current, and the reason we use an alternating current is because it's just more efficient compared to a direct current. With the power socket, you notice there are 3 different connections in the power socket, and this represents 3 different types of wires. There's an active wire, a neutral wire, and then a wire to the earth. For a normal circuit to be complete, you need a live/active wire that carries the electricity from the power source to your device. You need a neutral wire which carries the electricity back from the device to the power source. And then the earth wire, its main function is a safety feature. Its role is to strictly protect the device. It provides the path of least resistance for electricity to flow if there's a leakage within the circuit. And sometimes within these circuits, we can have a neutral earth bond, which is a special bond where the earth wire is connected to the neutral wire. And this ensures that the neutral wire remains at 0 volts relative to the earth, which is again critical for electrical safety. Now, on a side note, you'll notice that in the theatre, you have different colors of power sockets. You have red or blue, and then you have the white for cleaning purposes only. What differentiates the red from the blue is that the red power point is connected to a secondary power supply. So in case of an emergency, it will continue to work through a backup generator, which means that you might have the most tiniest of delays if the main power fails. Comparatively to a blue power socket, this is connected to a UPS, which is an uninterruptible power supply. And this provides an even higher level backup than a backup generator. So if there's a disruption to the main power supply, there'll be 0 disruption if your power socket is connected to a blue power point. This also means you should be cognizant of the fact that you don't put everything into the blue power supply, because it's going to take up a lot of energy from that uninterrupted power supply unit. So now that we know the basics of an electrical circuit and electrical supply to the operating theatre, we can then go on to look at what is microshock and what is macroshock. These are classifications of 2 different types of electrocution. An electrocution is one type of hazard associated with electrical safety. The other hazards are burns and fires. With regards to electrocution, the degree of electrocution or the damage caused by electrocution will depend on the current, the path it takes, the density, the type of current, whether it's AC or DC, and the duration of your exposure to that electrocution. What the terms macro and micro shock do is they divide the cause of that electrocution. So with macro shock, it's a large amount of current passing through a person that may lead to injury. And there's certain thresholds you have for the amount of current you need to cause an electrocution. So at low currents, such as 1 to 5 milliamps, here you might have no to little harm in a patient. When you get to 50 milliamps, this is where they say the threshold for pain is, and then you need exposure to 100 milliamps to induce VF if the current passes through the heart. Now the better question is, why would you get electrocution in the first place? And the reason is, if there's a leakage in that circuit we spoke about, and you happen to accidentally touch the active wire, or the patient is exposed to an active wire, they become part of the circuit. And what I remember most about electricity is that it likes to go through the path of least resistance. So if you become a part of this circuit, you become the path of least resistance as it goes from you down to the earth. And if that current is high enough, that's when you can get injury. In comparison, microshock is a small amount of current that's delivered directly to the heart and may instantaneously cause VF. And this can happen from devices that we place into patients, such as central lines or pacing wires. And because that current is directly in contact or in close proximity to the heart, you only need a small amount of current in the form of 0.1 of a milliamp to cause that VF. And this is an important number to remember because it sometimes comes up as an MCQ, but also all Viva examiners like to ask this number when they ask you a Viva on electrical safety. So then what do we do in the theatre environment to decrease the risk of these types of electrocutions occurring to ourselves or to the patient? Well, there's some really simple things that we do as part of electrical safety, such as insulating the wires so that they have a high resistance substance around them, decreasing the risk of you touching an active wire and then being part of that path of least resistance. There's fuses that will seize current flow if there's a high current that exceeds a certain threshold, and these are same to the fuses that you have at home. But you don't want to have fuses for everything in your operating theatre because you want to be able to run certain things even if there's a small amount of leakage occurring. So what's specific to an operating theatre are certain devices called residual current devices and line isolation monitors. Starting off with residual current devices or RCDs, these are monitors that balance the current between the live wire and the neutral wire. And if there is some current leakage to the earth wire, this imbalance causes the device to trip and cut power. They're really smart devices and they're used outside of the hospital system as well, and they can detect a current leak from anywhere between 5 to 10 milliamps. And once that current leak is detected, they'll cut power supply within 40 milliseconds. You can easily identify RCDs within the operating theatre because on the power socket it should say RCD protected, and typically the RCDs are linked to the red power points, and therefore they're usually linked to a secondary power supply, so they're not part of the UPS system. Then with line isolation monitors, this is slightly more trickier to understand, but what it's actually doing, I think, is very cool and really smart. It's creating, as its name sounds, a circuit which is isolated from Earth and so-called a floating circuit. The floating circuit refers to there being two circuits, a primary circuit which is part of the main circuit getting power from the power station, and then a secondary circuit which is not actually connected to the main supply. In this secondary circuit, it's important to note there's no such thing as an active wire or a neutral wire. There's just a wire 1 and a wire 2, or better yet, a line 1 and a line 2. These lines 1 and 2 are connected to a limb monitor, and that limb monitor is continually checking if those wires have any leak around them, and leak specifically going to the ground, because that floating circuit does not have a ground wire. It does continuous calculations and it detects when isolation from Earth has been breached. And when this occurs, instead of shutting that circuit down like an RCD does, the limb instead will set off an alarm to let you know that there's a breach or a leak in the circuit. And the threshold for setting off that alarm is a current leak above 5 milliamps. The reason you want limb systems along with RCDs is because limbs will allow you to continue using that power equipment without it shutting off abruptly, because certain things you don't want to shut off abruptly, like your ventilator. So this gives you a chance to notice that there's a problem and then figure out whatever way you want to then fix it or stop using that equipment. And just like RCDs were linked to the red power points, limbs are usually linked to the blue power points. And again, on those power points, you should have written on it line isolation monitor or limb protected. Then there's a third and final layer of protection against electrocution, which is very unique to critical areas such as the operating theatre. And this is the equipotential earthing system, or the EES. The simplest way to think about this is that you use large diameter copper cables to then combine all the earth points into one earth point, because each different earth point may have its own different potential difference. So by combining them all into one, it equalizes all the potentials of all the earth points. And this is mandatory in the operating theatre because it's the only type of safety system that protects against microshock. So therefore, it's a must, and you can see your EES in your operating theatre as usually a green knob at the back wall in your operating theatre room. Now that we've covered ways that we make the operating theatre safe from electrocution, we now have to cover how do we make the equipment we use safe for the patient. And electrical equipment safety can be divided into two parts. You have the first part, which is the classification of the electrical equipment itself, and then you have the second part, which is the classification of the applied parts of the electrical equipment. The applied parts refers to the parts of the electrical equipment that will actually directly contact the patient. Starting off with the equipment classes, there's three different types of electrical equipment classes. Class 1 refers to electrical equipment which is protected with an earth wire on the outer casing of the equipment itself. So the good examples from Mac 95 regarding this are things like refrigerators or the Anaesthetic machine. Class 2 electrical equipment are those equipment that are protected using a double insulated system. So this can be things like your portable ultrasound machine. Finally, Class 3 electrical equipment is protected because it uses really low voltages that pose really low risk of macro shock, and this is how your mobile phones are classified. Then looking at the applied parts, we can classify them again in three different ways. Type B are non-protected equipment that touches patient. So these can be things like the patient's bed that the patient can touch. So these allow a maximum allowable leakage of current of approximately half to 0.1 of a milliamp. They don't, however, protect from microshock, but they do protect from macro shock. Then we have type BF, which is the body floating applied part, and the symbol for this is a man in a box, and an example for this are things that we would apply to a patient like ultrasound probes for IV cannulation. These types of applied parts also protect from macro shock and allow the same maximum allowable leakage of current, and are used very commonly on patients, like when we apply BP cuffs to patients, so these would be classified as BF applied parts. And finally we have the CF type, which is the cardiac floating applied parts. This has a symbol of a heart in a box, and these are the only types of equipment that we can give to patients that also prevent microshock. So you can imagine that these are the types of equipment that would be inside a patient. So things like the arterial line cannula, or the central line cannula, or the central line wire, or a pacing wire. These things have to be CF type to be inside a patient, and you can see this classification system when you look at the back packaging of that equipment. In the same way the packaging has to display what that level of safety is for each type of applied part to that patient, so does each area within a hospital. And for specific areas in the hospital, specifically the operating theatre or critical care areas, they have to be at a level of protection which we call cardiac protected treatment areas. And the way you tell that again is through the symbol of a heart in a box. So because they need to be at that high level, what they then need to have is that EES system as our safety system within each operating theatre room. And if you're going to a rural or a remote site to set up an operating theatre, this should be something you're looking for to ensure that the things you're going to do invasively to a patient are going to be safe and not lead to an electrocution. So that's my brief summary of electrical safety and prevention and management strategies that we have within our operating theatre. And this moves us on to our next learning objective, which is outline the principles of surgical diathermy, its safe use, and the potential hazards. A diathermy is a device that's used to pass electrical current through tissues to generate heat in order to coagulate blood vessels or cut and destroy them. The mechanism of action behind this is that it uses AC current at really high megahertz, close to 0.5 to 2 megahertz, to generate heat within these tissues. The heat that's generated is proportional to the electrical power that's dissipated, and typically the electrical power behind these diathermy devices is close to 50 to 400 watts. The important principle you have to know here is this concept of current density. Current density is an equation which equals current divided by area. And if you have a high current density at the electrode, this causes more tissue damage. A low current density can cause heating without damage. So overall, there are two common types of diathermies out there. There's the unipolar diathermy and then the bipolar diathermy. The unipolar diathermy consists of a probe containing one electrode and then a large surface area plate that's attached to a patient. You'll see this in theatre as the blue plate that attaches to the patient. This is called the ground plate. The current density at the forceps or the electrode is really high, and this allows heating in the form of cutting or coagulating. But the current density at the ground plate is low, because remember, the equation for current density is current divided by area. And because of a large ground plate, there's little heating at this area. That's why when you take the ground plate off the patient, there isn't really any burns there. Then the second type of diathermy is bipolar. Bipolar consists of a pair of forceps with each point containing a separate small electrode. And the benefit of bipolar is that only a small amount of tissue between where the forceps is exposed to the current. Therefore, it improves safety. But because it's localized current, it's more suitable to control spot bleeding, like when you're trying to do precise surgery like eye surgery or neurosurgery, but it might not be suitable for big types of surgeries like your big laparotomies. In terms of the functions of diathermy, we've already mentioned that it can cut and coagulate, and the way it differentiates which one of these aspects it does is all based on the current waveform. So for it to cut, it uses a low voltage, typically 250, to produce a high current at a continuous sine wave. This continuous sine wave allows for rapid heating and boiling of that intracellular fluid. In comparison, coagulation mode uses a pulsed sine wave at a high voltage, close to 9,000 volts, with a current which is also higher, close to 1 to 1.5 megahertz, and this interrupted sine wave is essentially causing mini lightning to occur at the site of application, as well as drying of that skin tissue. You can also have modes that are a combination of coagulation and cutting, known as blended modes, and with these blended modes, you can pick different percentages of which one you want more of. Diathermy nowadays is very safe, but the first question you should be asking with regards to the main safety features is, why does diathermy, being a current that we're passing through the patient if it's unipolar, or if it's localized current in the form of bipolar, not affect the patient's heart? And this goes back to the currents that diathermy uses. Because of the very high current, these currents are too fast for the myocardium to then register and contract to. The myocardium's refractory period is too long to respond to the changes from the diathermy. Therefore, in most circumstances, it's very safe and is unlikely to cause VF. For VF to occur with diathermy, its frequency needs to be dropped down to ideally 50 Hz, because this is the frequency where you can really cause big damage to the heart. Now, the other problems with diathermy is that it's still a risk of causing burns to patients. It's an electrical equipment that's exposed to patients. What we get specifically worried about is high current density, specifically at that ground plate. If that ground plate isn't adhered right to the patient, then all of a sudden you're increasing the current density, and this can be a huge risk for a localized burn. Thankfully nowadays, the diathermy device usually won't work or will come up with a pop-up message saying attach ground plate if it's not adhered right. Other risks are simple things like it needs to be used by trained professionals. When it's being used and burning tissue, that tissue is creating smoke, which can be potentially carcinogenic to the people around it. The other main risk we especially get worried about is diathermy use in the presence of internal cardiac devices, specifically pacemakers and defibs, because diathermy can alter what those devices sense and can lead to an inadvertent shock or a change in rhythm. For this, we typically recommend to avoid diathermy use within 15 centimeters of the device location, and if this cannot be achieved, then we advise to use bipolar for the lowest duration possible, because bipolar is much more safer than unipolar, because unipolar will pass its electricity current through the patient's body until it gets to the ground plate. In keeping with diathermy affecting ICDs, you'll also notice when diathermy is used, when you look at your monitors, it might alter your ECG reading, your BIS reading, and potentially, although very unlikely, your pulse ox reading. So those are always easy points to remember if this gets asked in an SAQ. So those are all our LOs covered for today. However, there was one more learning objective which has since been removed in 2023, that was describe the principles of surgical lasers, their safe use and potential hazards. This is unlikely to be asked again, but I just want to briefly touch on it now because we'll incorporate some of the aspects of laser safety into electrical safety. To briefly give you an overview, laser stands for light amplification by stimulated emission of radiation. I was as surprised as you to first learn that laser is actually an acronym. The mechanism behind laser is that it uses an energy source which is passed through a lasering medium which is housed in a resonator made up of mirrors. The energy source can be an intense flash of light, such as a solid or liquid laser, or it can be a high voltage discharge, such as a gas laser. In passing this energy source through a lasering medium, the energy excites electrons within the lasering medium, and this places the electrons in an unstable excitable state. When more than 50% of the electrons enter this unstable excitable state, that's when you get to a critical threshold known as population inversion. And when this is reached, those electrons that are in their unstable excitable state fall back into their resting state, and as they fall back, they release a photon. The photon is the key thing for a laser to work. When a photon is emitted, it goes off into a random direction known as spontaneous emission. And if the photon hits another electron, that electron goes back into its resting state and then releases another photon called stimulated emission. These two photons now travel in the same direction and have the same wavelength and energy. And once you get this occurring, you can start to develop a chain reaction, and the chain reaction is called the amplification of light release. What the mirrors in the lasing medium do is ensure that the light is reflected back and the stimulated emission continues. Once enough energy has been built up in the laser, one of the mirrors is a partially reflective mirror, and the beam of laser is focused through this and aimed directly on the target. The laser travels in a single direction and causes localized heating and vaporization. There are multiple different types of lasers out there available, but we don't need to know that now. What is key is that you know that the laser light has some specific properties. One, it's non-divergent, meaning all the photons move in parallel. Two, it's coherent, all the photons are in the same phase. And three, it's monochromatic, all of them have the same wavelength. And these are key characteristics of laser. So then how does this work back into laser safety? If you've been in a theatre which has laser going, you'll notice that the scrub scouts take lots of precautions when laser is being used. There's a specific person that's put in charge to be the laser nurse, and the laser nurse is tasked with making sure the laser lights are outside in the theatre, alerting people that there's laser going on. They ensure that everyone in the theatre space has goggles on that are specific for laser safety, because laser as an energy source can damage your cornea. They also ensure that all the windows and blinds are covered when the laser is on. And importantly, when it comes to laser fires or electrical fires, you need the same three components available to ignite a fire. A fire is a chemical reaction that liberates energy in the form of heat and light. And there's three requirements for any fire. One, a combustible substance. For the patient, this could be the endotracheal tube or the drapes. The second component is an oxidizing agent, so a substance that can support combustion, typically oxygen or even nitrous oxide. And then thirdly, an ignition source. So this could either be a laser or a diathermy, something with high enough energy to cause an oxidative reaction. So if you remember these three requirements for a fire, you can then think of the requirements to decrease the risk of fires. For example, with lasers, you can use as low oxygen as available, typically less than 0.3 or 0.25 FiO2. You can use specific types of endotracheal tubes which are laser safe and the cuff is filled with saline. You can have syringes of saline available when you're using laser for airway surgery. You can protect nearby critical tissues using wet swabs, which is why you typically see gauze on patients' eyes being slightly wet as you place them on before the laser goes on. And then most importantly, for safety and prevention, before you use the laser or diathermy, you come up with a plan in the event there's an electrical fire, because prevention is better than the alternative. Now that officially covers all the learning objectives today, and like I said, laser is not really part of the curriculum anymore, and if you wanted to save time, you can omit that last part, but you'll have to learn it eventually in your Part 2 curriculum. Now we're going to move on and look at the past SAQs, of which there's not too many of, which is good because this is already a long episode, but of the ones that have been asked, majority of them have low pass rates. The first SAQ is from 2024 second sitting with a 40% pass rate, which was draw and label a circle breathing system, include a bellows ventilator, on your diagram show where a scavenging system is attached, and part B, describe how an active scavenging system works and the purpose of scavenging. Now this is a variation of a previous question asked in 2014, which was simply describe an active anaesthetic gas scavenging system with a 5% pass rate. But with this most recent variation of this question, the examiner report here is really helpful. In terms of the domains they wanted you to cover, they wanted you to correctly draw and label a circle breathing system diagram. And before moving on to the rest of the examiner report, remember that in our last episode, we said that the circle breathing system is the most efficient breathing system. It has some core components to this diagram, including unidirectional valves on the inspiratory and expiratory limb, a CO2 absorber, a Y connector, which at the point distal to this is where you start to get mixing and dead space occurring. And also with this system, you have a means of introducing fresh gas flow. There's lots of variations of different diagrams on Google when you search up a circle breathing system, but typically the bellows ventilator is placed on the expiratory limb. It's placed here adjacent to your APL valve so that when you switch over from manual, you go onto the APL valve of the ventilator. This ensures ideal scavenging, so you're removing the wasteful drugs, and then you're generating pressure to drive the flow from the expiratory limb into the CO2 absorber, so that you're clearing any waste products as it enters the inspiratory limb. Specific to this diagram, the fresh gas flow inlet is in the inspiratory limb, where it joins up with the rest of the flow and then goes to the patient, passing through the unidirectional inspiratory valve. The bellows system itself is a common anaesthetic ventilatory pump, where it drives gas typically with ascending bellows, which means that they rise upward during expiration. And this is simply because if a disconnection occurs within the circuit system, those bellows begin to fall, and you can recognize them as a visual warning aid when there is a circuit leak. Comparatively to older types of bellows systems, which were descending bellows that you may not see within your typical anesthetic machine, because those didn't have that same warning system of a circuit leak. So just to ensure that you have this diagram in your head, the flow sequence begins with fresh gas flow coming into the circuit, usually just before the inspiratory valve. Then you have the unidirectional one-way inspiratory valve as the gases go into the patient through the inspiratory limb, where they join the Y piece, which is the junction where mixing occurs. You have the expiratory limb going into the expiratory unidirectional valve. From here, you have an APL valve if you're on the manual circuit, but if you're on a ventilator, you have the internal APL valve of the ventilator itself. The ventilator fills during expiration, and then the bellows compress that gas and push it through the soda lime where CO2 gets removed, and then you return back to the original step where fresh gas flow joins in the inspiratory limb and a new breath is delivered to the patient. So that's the first part of this SAQ. The second part of this SAQ focused in on the scavenging system. And to complete this, we'll go back to the examiner report, which I think answers this very well. They mentioned that scavenging is coupled to the manual APL valve on the bag limb and the ventilator's APL valve equivalent. In a description of how active scavenging works, it's a low resistance tubing that connects from both the manual and ventilator APL valves to a reservoir chamber. The reservoir is opened at one end so that no back pressure can build up, and suction can entrain room air continually so that no negative pressure can be applied directly to the circuit. Suction is attached to the reservoir chamber, and the scavenged gases are vented out the roof of the hospital. There's safety valves present for any positive or negative pressure developing within the scavenging system. And with this description, you can go back to what we learned today, which is that mnemonic of the essential parts of scavenging known as collect the rubbish drugs, with the collecting system, the tubing, the reservoir chamber, and then the disposal system. And if you remember that, you could really get some additional credits with this SAQ, because they stated that additional points could be gained by having diagrams to enhance the description of scavenging, specifying the diameter of scavenging connections, remembering it has a specific 30mm connection so that you can't accidentally then connect the wrong things to it, and then recognizing the biggest problems with this answer was not realizing that scavenging is coupled both to the manual APL valve, which is on the bag limb, and to the ventilator's APL valve equipment. Fresh gas is being added continually to the circle breathing system, and this must have a means to escape. This is one of the functions of the APL valves. Scavenging is coupled to these to collect the waste gases, to prevent pollution to the operating theatre. The other good area to recognize is that scavenging systems are designed such that suction cannot be applied directly to the breathing system, and that's why they have those open apertures to entrain air. This is why the reservoir chamber is required, because it's distal to the point of collecting and transferring those gases. So there's no perfect model SAQ for this answer, but I think we've just gone through how you would answer this question if it was asked again, and certainly is a high likelihood given its low pass rate. Then the next SAQ was asked in 2020 second sitting, and this was that controversial SAQ of discuss the adverse environmental effects of anaesthetic agents in current use. This had an 18% pass rate, and I remember being an anaesthetic PHO hearing this question being asked in the exam, thinking, how the hell am I ever going to get through the part 1? Because this is something I never thought of, and in the examiner report, they said that the question required a basic knowledge of the terms of greenhouse gases, ozone layer, and global warming, and an explanation of how inhalation agents and intravenous agents affect the wider environment. I think if you were really good at bullshitting, you would have been able to get away with a 2 or a 3 in this question, and you could see majority of people got a 2. The things that they said that were well done were ranking the agents by degree of impact, acknowledging the large amount of non-recyclable solid waste products, mentioning the adverse effects of nitrous oxide upon the theatre staff, and the things that were done poorly were accurately differentiating between the basic terms and understanding the effects of propofol on the wider environment. Now subsequently, I think the user submitted answer on Mac 95 is the most simplest, straightforward answer that I would go to as my model answer, because this just has the definitions being greenhouse gas as a gas that absorbs and emits infrared radiation causing greenhouse effect, i.e. radiation from the Earth's atmosphere warming its surface, global warming being the gradual increase in the overall temperature of the Earth's atmosphere, and one of the main causes of this is emission of greenhouse gases, and then ozone layer being an O3 rich region in the upper atmosphere that absorbs UV radiation. Depletion by the ozone depleting substances increases UV radiation, which can cause detrimental effects like skin cancer. In terms of the gases and volatiles, it's simply broken down into that inhalation agents are all greenhouse gases and some are also ozone depleting, and they stay for a long time in the atmosphere, up to 20 years for desflurane as an example. The CO2 equivalent, remember we talked about the term CDE20, and you can compare that to the GWP20. You can use that in terms of equivalent of 1 Mach hour for common anesthetic gases, and then equate that to driving numbers, which we said was worst for desflurane, isoflurane, nitrous oxide, and then sevoflurane. The other environmental impacts can be those high risks of infertility, miscarriages, cancers, and congenital abnormalities. In terms of intravenous agents, propofol has an overall theoretical lower impact on global warming. However, you need to do a life cycle assessment for the production, manufacturing, delivering, usage, and disposal, and things like syringes and tubing all contribute to medical waste. There's potential evidence that propofol being put down the drains has a toxic effect on marine life, and then we don't know what the effects of the metabolites that are excreted in the urine are on the wider population. Moving on to our next SAQ with another low pass rate of 23%. This was asked in 2015, which was discuss the prevention of electrical shock in the operating theatre. The examiner report here I don't think was very useful because it simply stated that most candidates started with the definition of macro and micro shock. They frequently quoted typical currents required to induce VF, and a discussion of operating room electrical supply design features followed by electrical device design was expected. The rationale behind these designs and the limitation was also expected, and in the ER, many candidates only had superficial understanding of electrical shock prevention. Now there's a few model answers out there that help you answer this question, but I think personally from my perspective, you need to model this answer in your own way because this is such a peripheral topic so that you retain the information for as long as possible. You can start off with the definition of macro and micro shock, and then for me, I would actually start off with thinking about the prevention of electrical shock by describing what type of environment the operating theatre is. Starting off with the operating theatre is a cardiac protected environment, which is the heart in the box. So how do we achieve this comparatively to the rest of the hospital? Well, for this to be achieved, there needs to be at least 3 specific safety devices. The main one that has to be there for it to be considered a cardiac protected environment is your equipotential earthing system, or your EES. And simply, this is just a large cable device that sources and puts together all the earthing devices into one, and it's the only device that decreases the risk of microshock. Then you have the additional RCDs and limbs, which both have a place to play, and you can then connect that into the color coding system you have of your PowerPoints, because this is another safety feature within the operating theatre. From this, I would then go on to talk about the equipment that we apply to the patient and how we use this equipment to prevent electrical shock, by first describing how the equipment is classified in the class 1, 2, 3 system, and then the applied parts in the system of type B, type BF, and type CF. And I think if you do those things, it's more than enough to at least get a 2 and maybe a 3, and that's what my goal is for this question if it comes up. There's no way in hell I'm going to remember the ketamine nightmares model answer, and I know that that answer has been put in there so that you can actually read it and understand all the information. So in my mind, I've already made some game plan theory that if this question comes up, I'm just aiming to get a 2 or a 3, and I'm going to organize this question the way I've just laid it out. Even if I know more than what I've said, I just don't want to waste time here and then have to catch up time on my subsequent questions. With that, we get to our last SAQ for today, which I'm tackling again with that same game plan theory as the previous question. This question was asked in 2014 and again had a pass rate of 31%, which was, describe the principles of surgical diathermy. The examiner report here was very useless. It just told you a resource to read because the question itself was lifted as an exact wording of a learning objective. And for me, the Propofol Dreams answer here is the model answer to go to. You don't have to be as in detail as the Propofol Dreams answer, but the way it's laid out in terms of definition, principles, surgical effects of diathermy, types of electrodes, and potential hazards is a perfect way to encapsulate how to answer this question. In brief, we know that surgical diathermy is a device that's used to pass electrical current through tissues to generate heat in order to coagulate blood vessels or cut and destroy them. The main mechanism of action, or the principle behind it, is the principle of current density, which is that the amount of heat that's generated when a current passes through the body depends on current density, and current density is equal to the current divided by the area. In terms of types and surgical effects, you can change the order of these, and I would go with dividing the types first, being monopolar and bipolar, which we've already spoken about, and then the effects of diathermy being either cutting, coagulation, and blended. And this is all related to the waveforms of that diathermy, with the cutting being lower voltage and a continuous high frequency sine wave, coagulation being a higher voltage and a higher frequency, which is given in a short burst, and then blended, which is a mixture of the continuous and the damped sine waves. In terms of hazards, you can break this down into electrical burns, electrical interference, tissue damage, and diathermy smoke. And with this, never forget the 3 things you need for an electrical fire. You need some combustible substance, an oxidizing agent, and then an ignition source. And the ignition source can be either diathermy, laser, or anything that's electrical. And that will do it for me today, guys. I hope the people sitting currently all get Viva invites in the next week, and I'll be back with some live practice Viva demonstrations very shortly. So until then, best of luck with your studying, and I'll catch you guys next time on Count to 10.